Hello, this is Mr. McMurray again, and we're here in Chapter 3, Newton's second law of motion. Alright, once again we're going to go back and talk about Galileo though for a second. Galileo studied motion of objects sliding down ramps and things like that, and he kind of laid the groundwork for a lot of what Newton later came in and formalized in his three laws. But as he noticed things, he put things on the ramp, he noticed that as they went down, they did not go at the same speed. If you were to stop the balls at 1 second, 2 seconds, 3 seconds, 4 seconds, and 5 seconds, you would notice that they're getting farther and farther apart. Now, this was a little difficult for him to prove because he could only take speed and have stopwatches, things like that. He used things like his pulse and things like that. But he noticed that as they went farther down the ramp, they were not moving at the same speed. It wasn't constant. It was increasing. The speed was increasing as it went downhill. And so this was acceleration. And so Galileo basically came up with the concept that as things go downhill, they would accelerate. Now, technically, you could also argue the same thing is happening in reverse when you roll a ball uphill. They would get closer and closer together as they go uphill because they're losing speed, okay? And they would be slowing down or decelerating, all right? But the idea of acceleration then can include speeding up or slowing down. If we talk about an accelerator on your car, we're usually talking about the gas pedal. But technically, the brake pedal is also a accelerator. It would be a negative or decelerator, all right, but no one really calls it that. So we talk about positive acceleration, we're talking about speeding up, which is what we normally think of when we use the word accelerate. But it also can mean slowing down, okay, because you're changing the velocity also there, but you're slowing down. And so decelerating or negative acceleration, we might call it, is slowing down. So basically, the idea of acceleration, based on what Galileo came up with, is this. Acceleration is a change in velocity. Okay, if you remember from last time, or last chapter, velocity is speed and direction. So if you change the speed or you change the direction, then you are accelerating. So that means that there are three basic ways that you can accelerate. You can speed up. That would be changing the speed. You can slow down, which would also be changing the speed, but in the opposite direction. And you can change direction, okay? And so acceleration is any time you change velocity, which can be changing speed up or speed down, and changing direction. Any of those things would result in a change in velocity. Now, it's also not just the change in velocity, but the change in time. How quickly are we speeding up or are we slowing down? If you talk about cars, I can go from 0 to 60, that's our velocity or our speed, okay? How fast from 0 to 60 in how many seconds? Because if you can do it, all cars can go from 0 to 60, my pickup can, but it may take my pickup 10 seconds, where it might take a race car 1 second or 2 seconds, or a very small amount of time. All right, and so we would have different accelerations. Even though we're going from 0 to 60, same change in velocity, the amount of time is going to affect which one we would say has a greater acceleration. All right, and so we can have acceleration, can be speeding up, positive acceleration, or slowing down, negative acceleration or deceleration. All right, or we can change direction. Now, for example, if you're a racetrack at Texas Motor Speedway going around in a circular track, even if they keep their speed, meaning 150 speed, are they accelerating? Well, on the straightaways, if they're going in a straight line, then no, they're not accelerating. But every time they hit the curve, even if their speed stays constant, say 150 miles an hour, going through the curve, since they are turning, they are constantly changing direction, then they are constantly accelerating, because that is a change in velocity, because it is a change in direction. So just something to keep in mind there. You can change in speed or direction, or you can do both. You could slow down into the curve, so you're losing speed and you're changing direction. You would still be accelerating. Just two different ways at the same time. All right. Now, that was kind of some of the basic principles that Galileo set down. All right. Now, Newton took this a little bit farther when he made his second law. All right. So if we think about an object, okay, that's trying to move. Let's just say we have take some bricks here. Look, it could be a bowling ball. It could be anything you're trying to move. All right. And basically, we know that we push on the brick, we're applying a force, and that force will cause the brick to start moving, change in its velocity, and therefore we are accelerating the brick. Okay, but if I push twice as hard on the brick, what's going to happen to the acceleration? Well, if I push twice as hard, we would expect it to move twice as fast, and therefore twice as much of a change in velocity, and we would say that it accelerates twice as much. Okay, so it would double the acceleration. Right? If I put half as much force on the brick, what would we expect to happen? We would expect it to accelerate half as much. Okay, so the amount of force is going to change in a direct proportional way to the amount of force we supply. So we say acceleration is, let's go the line here, means approximately equal to or proportionally equal to force. In other words, if the force increases, the acceleration will increases. All right, and vice versa. If the force decreases or goes down, then we would expect the acceleration to go down, and that just makes sense. Okay, the more force we put on something, we'd expect it to accelerate faster. The less force we put on it, then it's going to accelerate slower, assuming it's the same object. All right, but there's something else that affects the acceleration of an object, and that is its mass. Okay, and this is something that Newton was also trying to explain. We know that mass controls the object's inertia. Okay, we talked about inertia in Newton's first law. Inertia is its resistance to change. If it's moving, it wants to keep moving. If it's stopped, it wants to stay stopped. And we said the amount of inertia an object has depends totally upon its mass. Okay, and so the more mass it has, the more inertia. Now, if we're trying to change the speed of an object, how's that going to affect the acceleration? Okay, now we can use the brick example here that we actually have the picture of. All right, so we put the same amount of force on one brick, or put the same amount of force on 2 bricks, or put the same amount of force on 3 bricks. Well, the more mass we have, and we put the same amount of force on it, is it going to accelerate faster, or is it going to accelerate slower? And the fact is that if we put the same amount of force, then the more mass we have, or the more bricks, we go to 2 to 3, it's going to accelerate less. Okay, we put the same force on 1 brick, it's going to accelerate a certain amount. But we do it the same amount of force on 2 bricks, which is twice as much mass, then it's going to accelerate half as much. Okay, if we do it with 3 bricks, it has 3 times as much mass, it's going to accelerate only 1/3 as much mass. All right, and this had Newton came up with the relationship between acceleration and mass. He says acceleration is inversely proportional, 1 over the mass. In other words, if this number gets bigger, the mass gets bigger, then the acceleration is going to be equal to less. Okay, just like 1/100th is less than 1/10. The larger the number on the bottom of the fraction, the smaller its worth. Okay, 1 piece out of more pieces is going to be worth a lot less. So basically, as the mass number gets bigger, the acceleration is going to go slower, assuming you apply the same amount of force. All right, so we have basically these 2 laws, and Newton took these 2 together and put them together into this formula, which says acceleration is equal to net force divided by mass. All right, and basically this is just a combination of these 2 proportions. In other words, if this number gets bigger, the amount of force gets bigger, and the mass stays the same. As this number gets bigger, the top number of the fraction, we would expect the acceleration to be bigger also, and it will accelerate faster. If the force stays the same and we increase the mass, then it's going to be inversely. The bigger the object with the same amount of force, it's going to accelerate much slower. And so that's basically what Newton's law is saying, is that as you increase the force, keeping the mass constant, the acceleration will increase proportionally. However, if you keep the force the same and increase the mass, then it will decelerate or only accelerate at a slower rate or inversely. So basically saying acceleration has a positive correlation with net force. If it increases, then so will acceleration. And it has an inverse relationship to the mass of the object, which means the bigger the mass, the less acceleration. Or the smaller the object, the less mass, the greater the acceleration. It will do the opposite. All right? And that's basically what Newton's first law established. Now, before we go on, I'd like to talk a little bit more about mass, just to make sure we are clear on mass and what mass is. Mass is the amount of matter or atoms that make up an object. How much matter or stuff makes up the object. Okay? It is not volume. It does not have to do with how big it is. Okay? For example, we could have an iron anvil, which is not real big, and it could weigh as much or more than a whole person could, depending on how big the anvil is. But this takes up a lot less space than the person, yet they could have exactly the same mass. All right, that has to do with density. Okay, this anvil has a lot of mass in a small amount of space, so we say it is very dense. The person is less dense because it takes a lot more volume of their body to equal the same amount of matter or mass as the anvil. So when we talk about mass, we're just talking about how much matter there is, not how much space it takes up. That's when we're getting into density, and we're not really talking about that. All right, and so we are also not talking about weight. Weight and mass are similar, okay, but they're not the same. Mass is how much matter there is. All right. Now, if something has a lot of matter, is it going to weigh more? Good question. It all depends on gravity. Okay, weight is totally dependent on gravity. If we have this anvil, and if we have gravity, say it was on Earth instead of out in outer space here, if it was on Earth, the gravity would be pulling it down toward the Earth, and it would have a certain weight. Okay, that's why we measure weight with scales, or scale, where you step on it and then gravity pulls you down. Or if you're in the supermarket, you put your fruit on the little tray and gravity pulls it down, and the scale measures how much does it get pulled down by gravity, and that's basically your weight. Now, if an object has more mass, is gravity going to pull it down harder? Yes, there's more mass for it to act on, and so the weight will also be good. So they're directly proportional. If you increase the mass, you also increase the weight, assuming that you're on Earth where gravity stays the same. Now, if we were to go to, say, we were to fly up to the moon, if we got out on top of the moon, is there any less mass to our body than there was on Earth? No, we still have the same amount of mass. So our mass does not change. But if we're on the moon is a lot smaller than the Earth, and it would pull down or have less gravity pulling on us, so we would weigh less. And that's why when you see the astronauts kind of bouncing around up there, because there's not as much force of gravity pulling down, but their mass is still the same. There's still as much matter making up their body as there ever was. Okay, so if we took things up to the Earth, say we had two objects that had the same mass, okay, if we took them up to the moon, they would weigh less, but if you put them on scales, okay, balancing a scale with a little thing here in the middle, they would still balance because they have the same amount of mass, and so there's less gravity pushing down on this mass, so it weighs less, but there's also less gravity on the moon pushing down on this side, so it also weighs less, and they will always balance. And that's why mass is measured in balances, because mass is always the same, and no matter where the gravity is, it'll change on both sides equally. Weight, they have way less, or if you went to Jupiter, they would weigh more, and they would still balance no matter where you're at. So we measure mass on a balance, weight we measure on scales. Weight depends totally on gravity, okay, and mass does not. Mass is the same no matter what. So instead of saying, oh, I need to watch my weight, maybe we need to just go someplace that has less gravity, and then we wouldn't have to worry about that. Now, the last thing is, we talk about forces and mass and weight. We need to know the equivalence of it. 1 kilogram, let's say you have 1 kilogram, that is a mass, a certain amount of mass. It looks like we'll have to finish this up on the next one. All right, so we'll stop right there, and we'll see you in the next part of our lecture shortly.